Hi, this is Thomas from Apex Game Tools. In this video we're going to look at dynamic grid updating. Updating grids dynamically is an alternative to using dynamic obstacles. Now, you may have scenes where you have otherwise static obstacles that you would like to either destroy or add additional static obstacles to your scene. You may have terrain that you need to change due to certain events, and for this you can use dynamic grid updating. So in this video we're going to look at three things. We're going to look at how you deal with static obstacles, how you deal with terrain, and finally we're going to look at how different height map and grid settings affect the performance of dynamic grid updating. So let's start by looking at obstacles. Now here we have a scene, as you can see, with 4 static obstacles, and we have a unit that will move around these obstacles in the manner you would expect. Now if we wish to remove some of these obstacles, obviously we would like the grid to update itself to reflect these changes. If we were to simply remove an obstacle, like just disabling it like this, as you can see, the unit doesn't respond to that. The grid doesn't know that this has happened, so it will not update this section and it will still see it as blocked. So how do we fix this? Well, we use dynamic updating. So in the scene we've also added a small bomb that I can spawn so that it will destroy obstacles, and we would like it to, as it did there, actually update the grid so that the unit knows of this change. So let's look at how we do that in code. Now this is the line that you need to look at. This is the only line you need. So to update the grid is quite simple. You simply call the update method. This method is available on a number of different types. In this case, as you can see, we're using the grid manager, and we pass it a bound struct, that is the area we want to update, and then we pass it a maximum number of milliseconds that we will allow the update to use per frame. So updating is not instantaneous. It will actually take some frames for it to update, and the time it takes depends on the size of the bounds and other parameters that we'll get back to in just a second. Now, as mentioned, we have different options. We have the grid manager. When you do it on the grid manager like this, it will actually update all the grids that are affected by this bounds. So if the bounds covered multiple grids, it would update all of these grids for the part of the bounds that affects that particular grid. You could also just call it on a specific grid. If you just have one grid in your scene, for instance, and you have a reference to that, you can simply call it on that. Now, when calling the update method, two things happen. The first is that the height map is generated again, or in that area. So if you have terrain changes, those will be updated. Now in our scene here we don't have any terrain changes, we just have the obstacles, and that is the second thing that happens, that it will look at that area and update each cell to reflect their new status, whether they're blocked or unblocked. So this is the most simple version of the update method. We have other overloads that take additional parameters, and we'll look at those now. So we'll move from this scene and we'll look at terrain instead. Now terrain is the same principle. You can add or remove or change terrain and have the grid updates accordingly. So in this scene we have, as you can see, blank scene initially, and if I start the scene I have the option to actually spawn a bridge in the center, and as you can see it will actually update itself so that the unit will now be able to use the bridge. So let's have a look at how that looks in code. It is pretty much the same thing, as you can see. This part is, again, it's just this one line that has to do with the updating. In this case I'm using an extension of the bound struct itself, so you can actually call the update on a bound structure directly. That's the third alternative: the grid manager, the grid itself, or a bound struct. Now, as you can see, in this method we actually use a few additional arguments to our function. We still have the maximum amount of milliseconds per frame. Then we have a toggle that controls whether or not I'm going to block the bounds that I'm updating while the update is happening until it's done. And then finally I have a callback option so that I can get a callback once the update has completed. In this case, as you can see, we just debug the amount of milliseconds that the update took. So let's have a quick look at that scene again. So now that I spawn my bridge, as you can see, the unit does react in time for it to actually not walk into the bridge, and then it will start using the bridge once the update is done. Now the update it took, as you can see down here, it took 634 milliseconds in total. This is not how long it actually took to update the grid, because we only used 10 milliseconds per frame, but it will have used about a third to update the grid. Now most of this is used updating the height map. And that brings me to the second part of this scene that has to do with performance of runtime updating depending on how the grid has been set up. Now here we have a very small grid, so we actually get the update done in time, though it doesn't take too long. But if we were to enlarge our grid, let's see what happens then. So let's enlarge the grid. Let's put it up to 4 times the size. We'll do the same for our grid, of course. So now we have a larger grid. Still have that same area that we need to update, the small bridge. So, well, shouldn't actually take any longer. Let's try and see that. Okay, let's try that again, and let's actually spawn the bridge. So I'm going to spawn the bridge, and as you can see, the unit just walks straight into the bridge, not recognizing that it has appeared. And as you can see down here, there it was. So this time it actually took 10 seconds for it to update the grid. Now that can seem a bit strange because it's the same exact area that we need to update, and it still took way longer. Now the reason that has to do with how the height map is stored. Now obviously this problem is only there if we are using a height map. If we use something else, for instance raycasting, there is no height map, so there is no change and no problem. So when I spawn the bridge, it will just instantly change its route, and it will instantly know that the bridge is there. However, if you are using height maps for height navigation, there is a second thing that has impact on how dynamic updates work, and that is how the height map is stored. Now this is toggled down here on the grid component itself. The default value in 2.0 is to use a quad tree. A quad tree has the advantage of only storing the height values that it needs to. So it basically only stores, in this case, because this is just one big flat scene, it only stores one height. So the quad tree is super efficient memory-wise in this case because it just stores one float. But it has a problem that quad trees cannot be updated partially. This means that basically a quad tree, you can think of a quad tree as a collection of squares, and in order to update a quad tree you will need to at least update one such square. In this case there's just one big square. So when I ask it to update, it actually updates the entire square. So that means the entire scene is actually recalculated for its height settings, even though we're just changing a small area in the middle. So that is, as you saw, super inefficient. So the gist of this is that if you use dynamic updating on your grid, you will most likely not want to use quad trees for storing. While this is very efficient memory-wise, it is not very efficient for dynamic updates. Now the alternative is dictionary. This was the default setting before 2.0. It uses more memory, but it is both faster in lookup, and it also supports dynamic updates much better because it doesn't have to update any more than what we actually ask it to update. So using that instead here, we'll basically have a similar effect as if it was not using a height map. As you can see, it just took 120 milliseconds to update. So it is a bit of a trade-off. Now obviously in this particular example, it's the worst case scenario basically, because we have a scene that is one height to start with, and that makes it the worst case possible for the quad tree. If you have a map with different heights all over the place, the quad tree will not have to update the entire grid. It will just update the squares that are affected by this area that we're updating. So in some cases it may be just fine to use the quad tree, in other cases it won't. So you will have to experiment with this, and it will depend on how your scene is set up, which method you want to use. Now let's just look at one of the second option to the update method, because that is one way of, well, partially solving this problem that we saw before. So when we go back to having the quad tree, and we saw that it didn't update in time, so that unit just went straight into the bridge. Now we can fix this by using this second argument, which has to do with blocking while updating. So if you set this to true instead of false, it will actually block the section of the grid that is currently updating while the update is in progress. So this means that the unit will ignore this area during the update. So let's try and see that. So now I spawn my bridge, and now it will be blocked and remain blocked until the update has completed, and once the update has completed, the unit will then be able to use the bridge. So there we go, and now it will use the bridge. So that's it for the terrain part, and finally we're going to look at a combination of using static obstacles and dynamic obstacles. So here we have a scene. We have no units here, we just have a wall, just a single wall section, just a normal static obstacle. And what we would like to happen here is, once the bomb hits this wall, we would like it to, as before, update the grid so that it disappears, it explodes and disappears. But we would actually also want it to actually explode, so it will explode into fragments that will then be spread across the map. Now these fragments are then dynamic obstacles. So here I have a fragment that I'm going to use for my wall once it is exploded. As you can see, it's simply a small cube, and I have a dynamic obstacle attached to it. So this looks like so. So I'm going to explode the wall, and it's going to explode into multiple fragments, and they will then block the grid where they land. Initially they will block a large area because they are in transit to their position, so flying debris, so units that would have been standing here would be aching to get out of there. So let's see how that is achieved. So the first part of it is exactly the same as before. We simply update the grid where the static obstacle was, and finally we then spawn small fragments where the wall was, and then we have those explode down here. So these small obstacles, as I said, have dynamic obstacles on them. The default is axis aligned. This is what ships with apex path. You can change these if you have the advanced dynamic obstacles package. You can change that to fixed hull, for instance, and have them update the grid non-axis aligned. Now in this particular example, it won't have that much of an impact because they are just smaller squares, so the difference between them being a little bit askew and straight axis aligned is not that big, but it will have a small effect even here. They will block less cells because they will only well, they will respect the alignment that they have when they land. So, and finally, let's just have a look at performance. The frame rate impact that we have when we do this, spawn these obstacles. As you can see, there is a small frame rate hit, but it is not that big, at least compared to a lot of other packages. So there you go. Dynamic grid updating. Hope that made sense. See you in the next video.